Okay, so find probability or the percent of juniors who scores no more than 90. Okay, mean is 74, so 90 would be above that. And we want the people who is no more than, which means it can be lower than or equal to. Okay, so we're looking for this section of the graph, which is good for us because the z-table tells us that section to the left of the value. So let's go ahead and calculate the z-score. So the value we care about minus the mean, mu, divided by the standard deviation of 8. Okay, so this one turns out to be integer, so 2 standard deviations above the mean. So we could use the empirical rule, but we could also use a z-table. Okay, so 2 is the same as 2.00. So using our z-table, 2.00 would be right here. So 0.9772. And then if we just convert that to percent form, that would be 97.72%. Okay, find the percent of juniors who scores between 58 and 74. Okay, so again, here's our mean, which for standard normal we're resetting to 0. So 74 is the mean. And then we also want to consider 58, which is somewhere below. Okay, so this is the area we want. Okay, so 58 will have a z-score of 0. I mean, we can do it if we want. It'll be, okay, the value we care about is 58 minus, oh sorry, it's the other one, that's 0. Okay, so 58 minus 74 divided by the standard deviation. Okay, so this becomes negative 16 over 8, or negative 2. Okay, so 58 is 2 standard deviations below the mean. And then calculating 74, okay, the value we care about is 74 minus the mean of 74. Well, that's 0 over 8, or just 0. Okay, so to get this, we could use we could split this up into, so the left half of the graph starting at the standard deviation of 0 away from the mean. Well, we already know this is 50%, but you could look up 0 if you're not sure. Okay, 0 is 50% of area to the left. Okay, but this is too much, right? Because this includes the whole tail to the left, and this problem does not want us to include the tail after, or I guess less than 58. Okay, so to cut off the tail, right, we would have to subtract it. Okay, so unfortunately this is a negative number, which our z-table does not have negative standard deviations. It only has non-negative, so we'll have to use symmetry. So I'll flip this horizontally. So the negative 2 would switch to positive 2, and then instead of shading to the left, now I'll shade to the right. Okay, so looking up 2 on my z-score table, again, it's 0.9772, but remember that's the area to the left. Okay, so to get the area to the right, I know the total area is 1.0000, so subtract the part I don't want, and I get that this tail is 0.0228. Okay, so the actual final answer, I take the 50% and I cut off the tail. So 50% in decimal form minus the tail that we're cutting off. Okay, so 47.72% of juniors scored between 58 and 74%. Okay, find the percent of juniors who scores at least 74. Okay, well, in this case, 74 is the mean, so at least means that score or more. Okay, so it's already 50%. We don't really need to do any calculation. Using symmetry, we know half the area is to the right. Okay, so score above 82. Okay, so 82 is more than the mean, so it'll be somewhere maybe over here. And we want the scores above that. Okay, let's go ahead and calculate the z-score first. The score we care about minus the mean over the standard deviation. Okay, so it's just one standard deviation above the mean. So again, we don't actually need the z-table, but just for practice. Okay, but again, z-table gives us the area to the left. So 1.00, 84.13% of the area is to the left. So to get the area on the right, I would subtract from 1. Okay, so about 15.87%. Okay, so 14 between 66 and 90. Okay, so z-score for 66. Okay, so -3, 3 standard deviations below the mean. And then, oh, wait, no, sorry. We're supposed to subtract from the mean. Okay, so the score we care about is 66. We subtract the mean of 74, right? The mean is given up to us up above, and then we divide by the standard deviation. So -8 over 8 becomes -1. Okay, let me see. Okay, and then the other value is 90. So that value minus the mean divided by the standard deviation becomes +2. Okay, so here's the area we want. So we can split this up. Okay, we could take this whole area and then cut off the tail. Right, this cut off this would give us that. Okay, so looking up 2 in our z-score table, we get 0.9772. Okay, we have to use symmetry again for the -1. So reflecting this would become +1, and we would now want the area to the right. So looking up 1 in our z-score table, we get 0.8413. So then to get the shaded area, the total area is 1, so subtract this from 1. So then the area we actually want would be the extra minus the cutoff tail. So 0.9772 minus 0.1587. Okay, so 0.8185, or in percent form, that'd be 81.85%. Okay. And then problem 15, probability a randomly chosen junior has a score below 74. Okay, so 74 is the mean, so below that is simply 50%. So next we have 23 through 25. Okay, relationship between the area on a normal curve for all x values less than a and the area under the normal curve for all x values greater than a. Student's response was both areas are 0.5 because the curve is symmetric. Okay, so this is only true if a is the mean, because then, yes, both sides are congruent and have equal areas. But if a is not the mean, say if a is over here, obviously this section is less than this section. Okay, so if this area is called P, the rest of the area would be 1 minus P. So these are not equal. Okay, so let's see. We have bags of apples, 5 pounds each. The weights are normally distributed with a mean of 5 pounds, standard deviation 0.25 pound. Inspector rejects all bags that weigh less than 5 pounds. Okay, so it says that it is supposed to be normally distributed, so it would look like this, with mean 5 and standard deviation 0.25. But then an inspector gets rid of all the bags that weigh less than 5 pounds. Okay, so this section is gone. So then it would look something like this. Okay, so this is the right half of the normal curve. Okay, biologist measuring lengths of frogs. Mean is 7.4, standard deviation 0.8. Does the data appear to be normally distributed? Okay. Okay, so just filling in this part first, right? We're adding 0.8 each time because that's the standard deviation. So plus 0.8 would be 7.4, plus another 0.8 would be 9. Okay, so then now the projected amounts. So if this range of values takes up 0.16, then we multiply that by the amount of objects, in this case 20. So we would expect 3.2, which is about 3. Okay, so how many values are actually near 6.6? Well, we'll do that later. Let's fill this out first. Okay, so half the area is here, so half of the 20 frogs means we expect 10 of them. Oh, I'm sorry. So we're looking for the values less than or equal to this. Okay. And then, okay, so if 0.84 of the area is to the left or equal to this value, we would expect 0.84 times 20 means we expect 16.8, or about 17. And then 0.98, so times 20, that'd be 19.6. So pretty much all of them. Okay, so we expect only one frog to be less than or equal to 5.8 in length, and that's exactly what we have. Okay, so we've already used up that. Well, let's leave it. Okay, so 6.6, we expect about 3 frogs to be shorter than that. So we have this one, and this one, and that's it. So far so good. Now we expect 10 frogs to be less than or equal to 7.4. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, pretty close. We'd expect 17 frogs to be less than or equal to 8.2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, matches perfectly. And then we'd expect all 20 frogs to be less than 9, which they are. Okay, so because the projected values match up very closely to the actual values, then it appears that this does follow a normal distribution.